Projectile motion that we talked about yesterday, we did a quick experiment with two ball bearings. It releases, the machine releases both of these balls at the same time. This one is projected horizontally and this one falls straight down. They both hit the ground at exactly the same time. So that leads us to what's happening to the motion. Both objects we decided fall downwards at the same rate due to gravity. We know that g is 9.8 meters per second squared. That's our acceleration due to gravity that we've previously calculated. So both of these balls, regardless of whether they are projected horizontally or dropped straight downwards, are subject to that same acceleration and therefore the same force in the downwards direction, which is why they fall at the same rate. But there must be something about this horizontal velocity, there must be something about that enables this ball to hit the ground at the same time as this ball, because we talked about such examples as if you drop a bullet and fire the gun at the same time, they'll both hit the ground at the same time. Obviously the one that you fire is going to be much further away from you, but they'll both hit the ground at the same time. So therefore this horizontal velocity must be constant in order for that to happen. So when we talk about projectile motion, we can really separate our motion into two parts. We can separate it into horizontal motion and also vertical motion, which is down here. So this ball that is moving horizontally has two components of velocity. This one's going straight down, so it only has a vertical velocity, but this one has both horizontal velocity because it's moving this way and vertical velocity because it's moving downwards. Its horizontal velocity stays constant, so if it starts off at say 10 meters per second here, then it's going to be 10 meters per second just before it hits the ground here in the horizontal direction. So that's never going to change. But the downwards velocity will change. It will increase because it's falling downwards, it's being accelerated downwards due to gravity. So we looked at an example, which was quite a long example, but as we saw when we went through this example, it wasn't too different from our usual equations of motion calculations. The time for the bomb to hit the ground, we can calculate that just using SUVAT in the same way. The range of the bomb, that's different. The final vertical velocity of the bomb, we can calculate that using SUVAT. The final horizontal velocity of the bomb, that was new as well. So as we go through this, we just write down SUVAT. We solve this in the same way. We drew this diagram, 100 meters per second. If it starts at that horizontally, then it will finish at that horizontally. This, because it's projected horizontally from a certain height, its initial vertical velocity will be 0. And that's always the case with things that are just projected horizontally. As we'll see today, things that are projected at an angle, their initial vertical velocity isn't necessarily always 0. So it complicates things a little bit. So we just use SUVAT. That's pretty much the same calculation as if it was dropped straight downwards. So we're looking at something being projected horizontally here, but equally we could drop something from this height straight down and it would be the same calculation, because we're only dealing with vertical velocity in that case. Here in B, where we're asked to basically find out what the range of the bomb is, the horizontal distance that it goes, which is across here, that's our range there. Then we need to look at both horizontal and vertical motion. If it's travelling at a constant speed of 100 meters per second in the horizontal direction, and we already know how long it takes to hit the ground, it's going to take the same length of time to hit the ground if we're thinking about horizontal motion as if we're thinking about vertical motion. So it was easiest there just to use basically speed distance time, or displacement equals velocity times time, to calculate out what that range was. Part C was just a basic SUVAT calculation without even considering that horizontal velocity. And then D, we already established that it was the same horizontal velocity at the end as it was at the start. The last part there was a wee bit more tricky, and we had to calculate out what the resultant velocity was. So we're taking into account that downwards velocity that we calculated as well as the horizontal velocity to give us a resultant velocity, and we can put a direction on that as well. So it's all about really treating the motion of the projectile in two different parts. Horizontal velocity is constant, vertical velocity is accelerating downwards due to gravity. When we're dealing with problems where things are just projected in a horizontal direction like this, vertical velocity, initial vertical velocity is 0, but we'll now move on to look at how it's different when we project things into the air at an angle.